All right, let's get into it. Today we're breaking down USO, a really interesting new unified model from Bytedance. And this thing is fundamentally rethinking the architecture of generative control. So if you're an engineer working in this space, believe me, this is one you're going to want to pay close attention to. So here's the plan. First, we'll look at the old dichotomy, the problem they're trying to solve. Then we'll dive into their synergistic solution. After that, we'll get into the weeds of building the USO model itself. Then, a little comparison, USO versus the field. And finally, we'll zoom out and talk about what this means for universal customization down the road. Okay, so for what feels like forever, the generative stack has treated two of the most critical user controls, I'm talking style and subject, as if they're fundamentally opposed. And this isn't just, some minor detail. It has literally dictated the entire architecture of the tools we build and use every day. So why the conflict? Well, the core engineering challenge has always been this. How do you get the style of one image and the subject of another without totally corrupting either one? It's a classic trade-off, right? If you want pure style, you have to throw out the subject's identity. And if you want to preserve that identity perfectly, you have to ignore the source style. This basic conflict has forced developers to pick a lane. You either build for style or you build for subject. And this conflict leads to two classic, failure modes that I'm sure you've all seen. On one hand, with style-driven models, you get what's called content leakage. This is where bits of the subject from your style reference just kind of bleed into your final image. On the other hand, with subject-driven models, you get style leakage. This is where unwanted bits of the style from your subject photos contaminate the output. It's a classic sign that the model's basically overfitting to the subject images. But here's where things get really interesting. The core innovation behind USO isn't some newfangled transformer block or a clever activation function. Nope. It's a fundamental reframing of the entire problem, from seeing it as a trade-off to seeing it as a synergistic partnership. And that brings us to the core idea here, cross-task co-disentanglement. It's a bit of a mouthful, but the hypothesis is actually super elegant. It asks, what if training for style and subject aren't conflicting tasks at all? What if they actually help each other? The theory is that by training a model to do both at the same time, you force it to get incredibly good at the one thing they both depend on, and that's cleanly separating content from style. And here's how that logic plays out. Think about it. To learn a subject, the model has to get really good at isolating identity features and, crucially, ignoring the source style. To learn a style, it has to do the opposite, isolate aesthetic features and ignore the source content. So the very features the model learns to include for one task are the exact same features it learns to exclude for the other. This creates this incredible, mutually reinforcing signal, and that's how it achieves a level of disentanglement that you just can't get with single-task training. Okay, so that's the big idea, but how do you actually implement something like this? Let's dive into the architecture, because this is where the theory really gets translated into code and, well, silicon. The whole implementation really rests on three main pillars. First, they built a massive, large-scale triplet dataset to give the model really clean learning signals. Second, they use a clever two-stage disentangled learning scheme. And third, there's a final style reward learning paradigm to really polish the output. All right, stage one is called Style Alignment Training, or SAT. And the whole point here is to teach the model to understand style as more than just, a texture or a color palette. We're talking about teaching it style as an abstract, semantic concept. The real goal is to align those visual style features with the model's already rich text embedding space. So how do they do it? Well, this style encoder is a Siglet model, which is a really smart choice. It's great at capturing those high-level semantic concepts like cyberpunk, not just simple textures. Then a pretty lightweight projector maps those features into tokens for the main model. And here's the critical part for efficiency. The main DIT, the diffusion transformer, is completely frozen. They only train the projector, which makes this whole alignment stage super fast and efficient. Okay, now for stage two, Content Style Disentanglement Training, or CSDT. This is where we finally introduce the subject. But the real magic here, I think, is how they hard-code the separation of information right into the architecture itself. It's a really elegant piece of system design. So for content, they use a standard frozen VAE. This gives a direct perceptual representation of the subject. So now the model is getting two totally distinct information streams. You've got the abstract style coming from Siglet, and you have the concrete perceptual content coming from the VAE.
And it's this clean architectural separation that's key to preventing that leakage we talked about earlier. And now they flip the script. The style projector from stage 1 gets frozen, and the main DIT is unfrozen for the full training.
And for that final bit of polish, USO uses something called Style Reward Learning, or SRL. Now, if you're familiar with RLHF, this is going to sound very similar. They basically use a separate reward model to score how stylistically similar the output is to the reference image. That score then gets fed back into the loss functions. You're not just minimizing a standard loss, you're also directly optimizing for the user's perceptual goal of great style fidelity. Okay, so that's the architecture under the hood. Pretty cool stuff. But the big question is, what can this thing actually do? And maybe more importantly, how does it stack up against the specialized tools that we're all already using in our tool chains? Well, for starters, the model's flexibility is right there in its super simple command line interface. I mean, look at this. It's a single command that handles everything. You can give it paths for both a subject and a style, or just the subject, or just the style. It's a really elegant interface that perfectly reflects that unified internal architecture we just walked through. Now, this table, I think, does a great job of positioning USO in the current ecosystem. The key thing to understand is that it's not trying to be a specialist killer. It's a powerful open-source generalist, and its killer feature is the tuning-free workflow. Sure, you could probably fine-tune Allura and eventually get higher fidelity for one specific concept, but that takes time. USO gets you, say, 90% of the way there instantly, right out of the box. So it's not about being the absolute best at any one thing. It's about masterfully balancing quality, efficiency, and flexibility. All right, for our last point, let's zoom out a bit and think about the bigger picture here, because the strategic implication of this work goes way beyond just another model release on GitHub. And this quote from the paper really captures the ultimate ambition. You have to see USO not just as a final product, but as a proof of concept for a much, much larger idea. By proving that style and subject control can actually help each other, they've laid the groundwork for a future where we could have a single model with disentangled intuitive control over, well, everything. Layout, lighting, camera angle, pose, you name it. So USO isn't the destination. It's the first really solid foundational stepping stone towards a true universal customizer.